This recording is for section 5.1. We are starting our last chapter, yay, of this semester, which is chapter 5. And we just finished up everything we need to know about derivatives, and we are moving on to those antiderivatives, which we started last week in 4.8. But now we're really going to dive into a little bit more of what the heck is an antiderivative really calculating for us, what kind of problems can we solve, why do we need them, and so on. Okay, so let's start off with our PowerPoint in 5.1. Here we go. Okay, areas and distances. So when we are calculating antiderivatives, we are essentially calculating areas or distance traveled. The area problem. Let's handle the area problem first. So we begin by attempting to solve the area problem. Find the area of the region S, and we see S is denoted here in this baby blue space that lies under a very specific curve. Let's call that curve f of x. And it is talking about the area under the curve from specific parameters A to B. So if we look at the picture, A is the start of where we start counting the area, while B is the terminal point in which we stop counting the area. So this means that S, illustrated by this figure, is bounded by the graph of a continuous function f of x and vertical lines, a starting point at A and a finishing point at B. Now, notice that the also, I would say it's a hidden boundary, is the x-axis. So whenever we are trying to find area, we are always taking it from the curve to the x-axis. Whether the curve is above the x-axis or below, it's always between the curve and the x-axis that we are calculating the area using antiderivatives. So for a rectangle, the area is defined as the product of the length times the width. You guys should know this, hopefully. The area of a triangle is half of that. So it's half of the width times length, but we just call the width and the length something different because we call the length of a rectangle the base, and the width of the rectangle is the height, which, notice by the picture, the height is always a vertical line perpendicular to the base. It's not necessarily one of the sides of the triangle. You can see that this is exactly half of a rectangle, which is why it's half length times width, or base times height. Now, the area of a polygon is found by dividing it into triangles and adding the areas of these triangles. That makes total sense, right? You'd find the area of this triangle, and then this triangle, and then this one, and then the fourth one. And you add up all the areas, you have the total area of the polygon. Makes sense to me. Example 1. Use the rectangles to estimate the area under the parabola y equals x squared with the set parameters of 0 to 1. So you can see the figure below. It is almost a perfect triangle. It looks like a triangle. And it's very likely that if we calculated this using the base along the bottom and the height as this vertical side here, that we would probably get a fairly good estimate, although we can tell that the area of a triangle would take a straight line from 0 to 1, 1. So there is a huge gap in the area here. And that's because this is defined by a curve and not a straight line. And therefore, we need to account for the fact that that's less area than the triangle if it had a straight hypotenuse. So we first notice that the area of S must be somewhere between 0 and 1 because S is contained in a square with the side length of 1, but we can certainly do better than that. So suppose we divide S into 4 strips, okay? S1, S2, S3, and S4, as seen in the picture below, by drawing the vertical lines at x equals 1/4, x equals 1/2, and x equals 3/4, as we can see. So essentially what we did was we picked a specific width. The width of each one of these slices is 1/4. Okay, I hope we can agree with that. And we always want the width to be the same. You don't want to do a quarter and then another rectangle that has a width of 1 and another rectangle with a width of 7/8. We want the width to be consistent. We can approximate each strip of the rectangle, each strip by a rectangle. So notice in the previous slide, these are not rectangles. The bottom three sides look like rectangles, but then the top is determined by the curve. Height is determined by the curve. But if we use rectangles, how that benefits us is that we know the area of a rectangle to be length times width. When these funky looking figures, we don't have an area formula for those. We would most likely have to take the area of the rectangle here and then try to take the area of the triangle, and we still wouldn't be very accurate. So we can see that if we took rectangles where notice the height of the rectangles are determined by the rightmost point, these are called right-hand rectangles, where the height of each one of these rectangles is determined by the rightmost point, not the leftmost point. Some cases, in this case specifically, we notice that the rectangles are above the actual function. So notice that this piece, this piece, this piece, and this piece here are all more than the area under the curve. And we would call this an overestimate because it is going to give us an area that is greater than the actual area we are looking for. In other words, the heights of these rectangles are the values of the function at the rightmost points. Okay, so if we had put here is the 1/4, we put a quarter into the function and we get a height. Okay, so remember the function was y equals x squared, so we're essentially putting a quarter into the function to get the y values of these points. So let me actually do that out with you so we can see how this is done, so it's not just done out for us. Jump into my whiteboard. So what happened is we have a graph with a y and x axis. We have our function, y equals x squared. We know that we are evaluating this function from 0 to 1, and we have chosen a width, which is denoted change of x, triangle x, to be a quarter. That's what was chosen. Eventually, I'm going to show you how to calculate that. You're not actually just going to randomly select a width. It's going to be calculated, but for now, it was just picked. So we break up 0 to 1 in 4 equal parts where they are a quarter thick. So we have an x value of 1/4. That means this first rectangle is going to be a width of a fourth, and then from 1/4 to a half is another quarter, and 1/2 to 3/4 is another quarter width. Oops. Go. And this last 3/4 to 1 is another quarter width. Now, when we draw the rectangles, we start, and when we want to do right-hand rectangles, so it's called a right-hand sum, commonly denoted RHS, right-hand sum, meaning we are calculating rectangles that the height is determined from the right side. So if I start on the right, I'm going to draw the first rectangle. I follow 1 up to its y value. And if I wanted to know this height, I would do y is equal to 1 squared, okay, which is equal to 1. So I put the x of 1 into the function y and got that this height here is at 1. So I draw the rectangle with a height of 1. Now the width is a quarter, the height is 1, so the area of this rectangle is going to be 1 times a quarter. Okay, does that make sense? I know I can't hear you, but I'm hearing you in my mind in the class saying, yes, that makes sense. Now, we can identify that this area here is an overestimate because there's more area in this calculation, which comes out to be a quarter, by the way. there's more area in this calculation than we actually need. We really only want the area under the function, under the curve. All right, let's keep going. Let's keep drawing our rectangle. So the next rectangle, we take the x value of 3/4, we find the height, the next height of the next rectangle, and we do that by doing y equals 3/4 squared, because our function is x squared. We square the top and the bottom and we get 9/16. It's a little over half because 8/16 would be a half. So this is 9/16 is the height of the next rectangle. And we then draw that rectangle. Again, we have some area that is an overestimate because we really only wanted the pink. Next rectangle is an x value of 1/2. Clear up some of this stuff that we have in my way. Okay, so to find the height at 1/2, we calculate y equals 1/2 squared, which gives us 1/4. Okay, so the height of this next rectangle is going to be at 1/4. So here I go up to this point here because this is the 1/2 and the height of the function is right here. Come over, this should be at the quarter marking. Draw my next rectangle. Again, I'm going to have an overestimate. I have some area that's not a part of what's under the curve, but most of it is what's under the curve. My last rectangle, my fourth rectangle, will have a height of y when x equals a quarter. So I put a quarter into the function, y equals 1/4 squared, which gives us 1/16. So the height of this last rectangle is 1/16. And I draw my last rectangle, again with some of the area overestimated and most of the area underneath the curve. Now, how do I add all this up now that I have all my y values and I have all my widths are all 1/4? I erased a lot of my y values, so let me try to put them back in. This one here was a quarter. And the one before that was 9/16. That was this one. So this one is 9/16. Okay, so we have heights of 1, 9/16, 1/4, and 1/16. And the widths are all the same. The widths are all a quarter, right? The difference between each of these x's is always a quarter. So let's talk about what this looks like to add up the area. So now that we have all our rectangles, we want to find the area of each individual rectangle and add them all up like we would with that polynomial example. Erasing. Okay, let's try this. So my first rectangle has a width of a quarter and a height of 1/16. So length times width, rectangle 1, plus my second rectangle has a width of 1/4, but a height of 1/4. So length times width for the second rectangle. Plus my third rectangle has a width of a quarter and a height of 9/16. Plus my fourth and final rectangle has a width of a quarter. More room. Width of a quarter and a height of 1. Now we put this in our calculators. We put in 1/4 times 1/16. Now remember, when you're doing fractions in the calculator, it is best practice to put your fractions in parentheses to make sure that order of operations happens how you want it to. So we have 1/4 times 1/16 plus 1/4 times 1/4 plus 1/4 times 9/16 plus 1/4 times 1, which we should hopefully know that that's just going to be a quarter. And this comes out to an area of 0.46875 is what my calculator is telling me. If I hit math, enter, enter, I get the exact area of 15/32. Now remember, because we have overestimates, when we're asked if this is an overestimate or an underestimate, this one is an overestimate because the rectangles exceed the top of the function. And we'll see in some of our examples that that's not always the case. If we did left-hand rectangles in this particular case, we would have unused area under the curve and it would be an underestimate. Back to the PowerPoint. Okay, so this example is showing exactly what we just did. They're putting the x value into the function. I did that separately and then produced y values. And this comes out to exactly what we just calculated, 15/32. And it is an overestimate because the rectangles exceed the function on top. Notice that if we did left-hand rectangles, here are the left-hand rectangles. Let's actually do those out using this function so you can see the difference. So again, we're looking at the same function. Y equals x squared. It's our x-axis and our y-axis, and we're using the same width markers. So we're evaluating from 0 to 1, and we broke this up into 4 even parts. Each of these parts has a width of 1/4. Now this time when we go to calculate our rectangles, we will be using left-hand points. So we start on the left-hand side here at 0. Now 0 is the very first marker and the height of the rectangle at 0, the height of the function at 0, 0. So the very first height is 0. So your first rectangle has no height at all. Now we can clearly see that this is an underestimate because this yellow area here is not being accounted for. The area of the first rectangle is 0. 1/4 times 0 is 0. The next height, we take 1/4 and we find the y value at 1/4. So we're trying to find this y value. Again, we would do that by doing y equals 1/4 squared, because that is the function that we are working with, x squared. And that came out to be 1/16. So the height of the second rectangle is 1/16. We draw over. Again, we can see above this rectangle that there is area unaccounted for, underestimate. The next rectangle, we use the x value of 1/2, and we have to find this y value at 1/2. Now we've already found these y values, but they're for different reasons now. Okay, so let's actually, oh, I didn't have to rewrite that whole thing. I could have just replaced the 1/4, but oh well. Okay, so now my height is found by y equals 1/2 squared, which gives us 1/4. So the height of my third rectangle is 1/4. Okay, draw across. And we can see that there is area unaccounted for in this calculation of this rectangle. Our fourth rectangle will be determined by a height of 3/4. So we're finding the height at 3/4. And if we square 3/4, we got that 9/16 height. And when we draw over, again, we have all of this unaccounted for area. So we are definitely calculating an underestimate. We are only going to get the area of the rectangles, which is leaving out some of the other area. So now let's calculate the area of these left-hand sums. Okay, so these are called left-hand sums because we're starting at the left side, abbreviated LHS. So we take the width, which remember the width of all of these rectangles is 1/4. All of them have a width of 1/4. So we're trying to find the area, and we get the first width of the first rectangle is 1/4 with a height of 0, plus the width of the second rectangle is 1/4 with a height of 1/16, plus the width of the next rectangle is again 1/4 with a height of 1/4, plus the last rectangle has a width of 1/4 with a height of 9/16. We put this into our calculators. Get my calculator. I do 1/4, 0, which is kind of pointless. It's going to be 0, but I'm just putting it in. 1/4 times 1/16 plus 1/4 times 1/4 plus 1/4 times 9/16. I get the sum of, hold on, I need room because I ran out of room here. Okay, so we get, this is equal to 0.21875 is the area. Let's see if we have an exact for that. So I go math, enter, enter, and I get an area of 7/32. Okay, so the overestimate was 15/32. The underestimate, and again, we know it's an underestimate because of all this yellow area that's not actually accounted for. So we would call this an underestimate. So the overestimate was 15 30-seconds. The underestimate is 7 30-seconds. There we go. So you may think, well, what if I average those together? That's actually not a bad idea. If you take your overestimate of 15/32, and you take your underestimate 7/32, and you average them together, you get a much more accurate. You are pretty much averaging the over and the under estimates. So if we add them together, we get 22/32, and then we divide by 2. Okay, then we get 22/32 divided by 2. We get 0.34375, which math, enter, enter. We get 11/32 would be our best estimate, as it is an average of the over and under estimates. So that's the difference between right-hand rectangles and left-hand rectangles. It all has to do with the height of the rectangle is calculated from where. So you can see the left-hand sum, and it's called L4 because there are 4 rectangles. Comes out to be 7/32, as we found. And they also suggest that the area is greater than our underestimate, but less than our overestimate, somewhere between there. Okay, if we increase the number of rectangles we're using, we are going to reduce the amount of area that's overestimated or underestimated. So the more rectangles we have, the more accurate we get. Okay, if we did 8 rectangles instead of 4 rectangles, notice the gap between the values are getting closer together. There's less room for error when we increase the rectangles. And we can see that in this chart here. So if we increase the number of rectangles to be 10, notice that now we've reduced the gap down to 0.1. We increase the rectangles to a count of 20. The gap has been released to 0.05 and so on. Okay, if we use 1,000 rectangles, notice that the gap is almost non-existent. We're up to now the third decimal place to find a difference. And that is essentially exactly what Riemann sums do. They eventually, right now we are just in estimation phase, so we are going to stick with just an integer number of n, but when we do full-on integration, we will be setting that n to go off to infinity, to be infinite number of rectangles, which then is exactly the area under the curve, which is the definition of an integral, which we will discuss as chapter 5 progresses. And we can see that in this diagram. Notice that the overestimates, how big they are, the amount of area drastically decreases as n, the number of rectangles, increases. Okay, so when we wanted to find that width, here is exactly how the formula is that I told you we would have a formula for. So the change in x, or the width of every rectangle, will be found by taking the terminal point B, where we're ending the area, subtract A, the initial point where we begin the area, and divide it by n, the number of rectangles we desire. So we get to choose n. For you guys, you don't get to choose anything because I'd be choosing it for you, or a WebAssign will be choosing it for you. And you would do b minus a divided by the number of rectangles they suggest, and that will calculate the width of each rectangle for you. Okay, let's do an example. So this is just more notes for you to read. See if we have another example in here, or if that's the only one we have. Oh, it looks like that's the only area example that we have. Okay, so let's attempt to do a different type of problem, but with the same concept. So we're not changing our concepts. We're doing left-hand and right-hand sums, but this time instead of calculating area, let's calculate a distance problem. So now let's consider distance. Finding distance traveled by an object during a certain time period if the velocity of the object is known at all times. If the velocity remains constant, then the distance problem is easy to solve, okay? Because distance is rate times time, in our case, velocity times time. But if the velocity varies, it's not as easy as just the basic distance equals rate times time. So if you were, for example, doing a linear speed, so you're on the highway, you set your cruise control to 60 miles an hour, and you never touch the brake or the gas pedal, then you can calculate your distance by 60 times however long you were driving for, and you'd know exactly how far you've driven. But in the real world, we would not be going 60 miles an hour the entire trip. We have to hit the brakes sometimes. We may want to increase the speed if we get into open uncharted roads. And therefore, now we have to account for the variation in speed. And that is a little bit more tricky than a basic formula. Let's suppose the odometer on our car is broken and we want to estimate the distance that we drove over a 30-second time interval. Okay, we take speedometer readings every 5 seconds and record them as follows. So because our cars are not in Europe, our miles per hour, our speed or velocity, is going to be in miles per hour, and we are counting in seconds. Now, right off the bat, we have a problem because we have a chart that has mismatch labels. Remember, our units always have to be the same. So I see that time is calculated in seconds, but our velocity is miles per hour. Instead, we need it to be per second. And typically, when you are talking about seconds, you no longer are talking about miles. You typically do velocity in feet per second. So let's recall dimensional analysis on how do you convert miles per hour to feet per second. So let's actually do this out because it's probably been a while since you guys have done this. ever. So in order to do a conversion from miles per hour to feet per second is what we're trying to set up, right? So you always start with what you know. So we know miles per hour. Let me take the first value in the table. So the very first value that was calculated in miles per hour is 17 miles per hour. So 17 miles per 1 hour. Now, I need this unit to be feet per second. So the first thing I need to do is get rid of the miles. Okay, so I need a conversion factor of how many feet are in 1 mile. So if I look that up, because a lot of you may not know, but there are 5,280 feet in a mile. So this is called a conversion factor right here, this fraction, 5,280 feet over 1 mile. Now, the reason why I have the miles on the bottom here and not at the top is because it needs to be diagonal from this mile so that they cancel when I do dimensional analysis. Now, my next focus is going to be that hour. That hour needs to turn into seconds. So because hour is at the bottom, that means that I need to put hour at the top in my next conversion factor so that they cancel because they are diagonal from each other. Okay, that's the yellow is telling you where I'm going with this, but hours, and we need to relate it to seconds. Now, in the real world, we may have to do a couple conversions for this one, hours to minutes and then minutes to seconds, because you most likely know how many minutes are in an hour and how many seconds are in a minute, but you may not know how many seconds are in an hour. So we have 1 hour. How many seconds do we have? Well, that would be 60 times 60 because there's 60 seconds in a minute and 60 minutes in an hour, which gives us 60 times 60 or 3,600 seconds in an hour. Now we see that miles cancels, hours cancels. What's left is feet per second. So we can see that feet per second is left. So we multiply straight across. So what we end up getting is 17 times 5,280. We're multiplying straight across. And that gives us 89,760 over, now we multiply 1 times 1 times 3,600, so that gives us 3,600. And we take 89,760 divided by 3,600, and we get 24.93 feet per second will be what I would rewrite the new table. I would probably round to 25. Okay, so I would say approximately 25 feet per second was the first calculation after the first bout. That's how fast I was going when I initially started. You would have to run this dimensional analysis for each one of the values in the table. So here we're looking at 17, 21, 24, 29, and we would have to calculate each one of these by doing a conversion using dimensional analysis is the easiest way. There are other ways to do it, but typically find that dimensional analysis is the best. So you can always Google dimensional analysis and find a video on it if you need a little extra reminding. So all of these values were changed based on what I just showed you. Now, during the first 5 seconds, the velocity doesn't change very much, so we can estimate the distance traveled during that time by assuming the velocity is fairly constant. So if we take the 25 feet per second and multiply it by the 5 seconds of time interval that we were recording, approximately we have traveled 125 feet. Okay, similarly, during the second time interval, the velocity approximately constant, and we take the velocity to be 31 feet per second is the next y value, and we multiply by the interval of 5 seconds that we were recording, and that comes out to be approximately 155 feet. So essentially we are doing these rectangles. We're doing length times width, where the width is the time interval of 5 seconds that we keep recording, and the length is the speed that we estimated that we constantly drove for those 5 seconds. Now, if we keep doing this to every single one of the speeds times the time interval, we add them all up. Notice that the very far right value, so we see that we used 25, 31, 35, 43, 47, and 46. If I go back to the table, we can see that that is every one of these speeds except for the 41. That means we were doing left-hand sums. When you do left-hand sums, you start all the way to the left and you do not use the last one on the right. If we were doing right-hand sums, you would start on the right and you would not be using the very left value if you were doing right-hand sums. So here's our left-hand sums. You start with the leftmost speed. Notice they're all times 5, and that's because the interval time does not change. And that gave us approximately 1,135 feet. Now, without a picture, it's really hard to determine whether that's an underestimate or an overestimate. The easiest way to determine this is to calculate the right-hand sum. Whichever number is biggest is the overestimate, and whichever number is smallest is the underestimate. So let's do the right-hand sums together. You're going to want to have that, you're going to want to have the chart in front of you so you can follow along on where these numbers are coming from. So if we wanted to do the right-hand sums for this problem, then we start with the rightmost speed, which is 41. And we're again saying that we were going 41 feet per second for 5 seconds. Plus, the next one from the right is 46 times 5 plus 47 times 5, always times 5 because the time interval doesn't change. 43 times 5 plus 35 times 5. So if you're looking at the chart, you'll see I am just going from right to left. Plus the last one, 31 times 5. Again, we don't do the 25 because these are right-hand sums. We pop these in our calculator. We have 41 times 5 plus 46 times 5 plus 47 times 5 plus 43 times 5 plus 35 times 5 plus 31 times 5, and we get 1,215 feet. Now we need to compare that number to the number that we calculated with the left-hand sums. So if I go back, or if I take a look, that was 1135. So the left-hand sums gave us 1135 feet. We just found with the right-hand sums, we have 1215. So now I feel much more confident making the conclusion that this left-hand sum was an underestimate and the right-hand sum provides an overestimate because this number is bigger than this one. Okay, and they show us the right-hand sum here. And then between the comparison, we can make an over-under estimate decision. That concludes section 5.1, practicing left-hand, right-hand sums given a function in a graph or given a table.